So our concept review for Chapter 4 is essentially deriving these relationships. So it really doesn't, hopefully we'll get out of here, might get out of here early, but we'll see. You need to start in each derivation of each relationship, right? Like for example, any system is heated or cooled under constant pressure. All these we're deriving entropy relationships. So what's the mathematical symbol for entropy? It's
S.
big S. Right? So there it is right here. So for each of these, you're heating or cooling under constant volume, constant pressure, right? Or it's isothermal, right? All these different processes. We're going to start here and derive a relationship, delta S equals, and so we'll use that for the homework. So for the homework, we won't be deriving these. We'll just use the end relationships, okay? But the exam that's coming up, I could very well ask you to derive those relationships, okay? So for the homework, you don't need to derive them all. But. Okay. So we are supposed to start, we're trying to find the entropy of a phase transition at the transition temperature. So we're supposed to start with this relationship. ds is dq reversible all over t. And then clue, set dq reversible at delta H. TRS probably stands for what? Transition, right? So transition, you're melting, you're freezing, you're boiling, right? The enthalpy, like enthalpy of vaporization, enthalpy of fusion. So delta S is really the enthalpy of the transition all over the temperature of that transition. Not so bad. But why can you do this? What's the REV? In this definition from the very beginning, it's reversible. So mathematically, it's saying every single bloody transition, phase transition, is reversible. Is that true?
Yeah.
They're all reversible.
What would you call the opposite of sublimation?
Gosh, yeah, solid condensation. All right, that's a good question. That's probably why they have words like fusion. You don't have to mess with it. So we're done with the first one. All phase transitions are reversible. They're
So because of that, that means that Q can equal delta H?
Yeah, so that's exactly what this means. This means that Q is equal to the enthalpy. How do you calculate the enthalpy? That's why they have a special little TRS down there. You look up the right enthalpy of the transition. And if they want joules, you pretty much have to multiply this by the number of moles, right? Because Q is rarely per mole. Q is always so many joules. So it'd probably look better if you did something like that. But just watch your units, right? It'll tell you. Okay. Any system is heated or cooled under constant pressure. So we're supposed to start. Whoop. Well, I guess I started on the wrong side. Right, my infinitesimal change in entropy is dq reversible over t. So the question is, it's constant pressure. Well, let's not put the d's in there yet. That might help you.
If pressure changes, can you have an entropy change? I mean, if pressure is not changing.
Well, we'll find out if we get a number for this.
Yeah, that's what I was going to say. It's like ds
Okay.
equals 0.
If you want to find heat under some process under constant pressure, and we're talking about gases, that's all we ever really talk about. What did we have for gases where you multiplied this constant pressure parameter times the change in temperature? You got Q, right? Something that tells you it's constant pressure, and you could look these up for gases, and it's constant pressure, and you could say, oh, it's going to take this much heat to heat capacity. What was the symbol for heat capacity?
Big C.
Big C, little p, and we should keep going, one more, little m for molar. Okay, so that's if we were after a macroscopic change. But we're not after a macroscopic change. We're after infinitesimal, a differential. So you should make that a D. I need to make what a D on the other side?
Delta T?
The delta. Not a macroscopic change anymore. Infinitesimal change. Okay. And I guess if to make our units work out, let's not have Q in per mole. What should I add to my equation right here? A little n. Good. You're following me very well. Okay, there it is. So let's substitute this. Let's substitute 1 into 2. My numbers are kind of odd, but that's all right. So let's just substitute one into the other one. So I'd have ds is ncpm dt, right, all over t. Now notice at the top, we're trying to derive entropy relations for specific changes. That means get something in the order of delta S equals blah, 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 right, for different processes. Well, how do you go from a differential to a macroscopic delta? You got to integrate. So we'll integrate both sides. And you can, I don't know, if you want to be really technical, right? S1 to S2, the initial entropy state to the final entropy state. You don't really need it, but what would the other side go from? T1 to T2, or T initial, T final, whatever symbols you like to use. Okay. So my delta S, S final minus S initial, or S2 minus S1, is going to be, what can I?
Pull out your NC.
Yeah. Now, when you pulled out that NCPM, this would be a good conceptual question. You're assuming what?
They don't change.
That heat capacity doesn't change over that temperature range, whatever you're interested in, T1 to T2. You're assuming that heat capacity does not change over that temperature range. And I'm left with 1 over T dt. Okay. So Shelby, how do I finish this then? Delta S is going to be NCPM, well, maybe not finish, but ln of T, evaluated from T1 to T2. Right? Take the derivative of the natural log, you get 1 over. Okay. So if I want to write a final expression here, Gloriana, what would it look like? Delta S is NCPM. Put in, well, just put in, make it an intermediate step. Put in the first one, then minus the second one. So it'd be the ln T2 minus ln T1. So you got off. Someone else, Alyssa has to remember it.
You can do like the ln of T2 over 2.
That's it.
Sorry. You said that. No.
There's my relationship. For any system heated or cooled under constant pressure, you can find the entropy for that change involving a gas. So, Jeff, how would you mess with the next one then? Now we're heating or cooling a system under constant volume.
Yeah, could you do like the QVM, or QV equals C?
What's QV? I'm not
Yeah,
sure.
CVM. CV delta T or something.
Heat at constant volume.
Yeah, so how would you start out? How would you start out? What would you change?
I don't know.
Anybody help him out?
DQ, right?
DQ reversible. Well, I guess, you'd start out here, obviously, right? You can't skip anything.
It's equals like n CVN delta T.
There you go.
That's what you were saying.
Yeah.
All right. Just change CPM to CVM. Okay, so you still got to, so I'll give you some time here. Just finish out the rest of it, right? Drive the relationship. Essentially, all you're doing is changing CPM to CVM, but and then finish the rest of it and drive your relationship. You get it? We're good? Kelly, you got it? Okay. A gas undergoes an isothermal expansion or compression. And we know the initial and final volumes. So we have to start with ds dq reversible over T. So that's our definition that we're starting out with. Always true. Reversible exchange of heat. And what's the temperature as that heat is being exchanged?
It's isothermal. Delta T 0.
If it's isothermal, delta T is 0. Yeah. So if you want to show a final answer that the answer is 0, well, we still have to work this out. If you predict that it's 0.
Would you do like?
What is 0? What else is 0?
Q.
What is 0? When it's isothermal, right away we
Delta U.
delta U. Delta T, you can say delta T is 0. That's right. But if it's isothermal, that was a hint. Because remember, we're after Q here. And the reason why I would go after U is because you know that U is what plus what? Q and W. And there's our Q. So maybe we can get it out of this. Right? So if it's isothermal, delta U is 0. And then, Kelly, we know delta U was what plus what again? Q plus W. So that has to be 0. So my Q is going to be negative W. Right? So what we need to do is this ring a bell? Isothermal expansion. Isothermal. You know the initial and final volumes. Work.
At whatever time delta V.
Negative W,
No.
negative W equals nRT, negative nRT ln V.
Yeah.
That's right.
Did you remember this? W is negative nRT natural log V final V initial. We need to derive that. And then we'll derive it, and then essentially we'll multiply it by a minus sign, put it in up here. Okay? And we'll have it.
If we derive it, wouldn't it be W equals negative pressure expanded times delta V? Because remember when we
Okay, when you derive it,
That's not what I was trying to think
when you derive it, okay, so let's start isothermal. Okay, and this is it's infinitesimal, so we're talking about reversible.
Remember on that one?
Where did we start?
question
W is
negative
Yeah. Yeah.
the equation for work. Work is minus
I see what you're saying.
P external times delta V. That's where we started to derive this. So, and then the next step, you would say infinitesimal steps, you'd say dW is minus P external dV, right? So see if you can derive that relationship.
Oh, and then px is nRT.
There you go.
Yeah, that's good.
Yeah.
That's how we got that,
Because
that equation.
because P is nRT. That's how we got the nRT in
Yeah,
there.
it's the same equation.
Exactly.
Worked out. So it's ln p.
Because we need to get how P is dependent on volume. Because we're going to integrate over V. So that we can't pull P out of the integral. P is a function of volume. So we have to substitute in how it is a function of volume before you integrate.
So it's just going to be that expression positive. So once you get that Q expression,
Yeah, hang on. We got to get everyone to catch up with you here. Anyway, everyone get it? Do you remember how to do this? Integrate both sides. Right? And it does not make sense to do this because you can't say initial and final states for work. You're talking, then it makes it look like a state function. Makes it look like an exact differential. It's not.
just
Path dependent.
It's just reversible
So you just
to
kind of leave it there.
macro. Is that what it is?
Yeah, kind of. You get it's path dependent. So you get your work here, your W. And then negative nRT all over V dV. Here where you can put your V1 and your V2. You can pull the nRT out, right, because it's supposed to be isothermal. So T is a function of V2, so you think, man, you got to plug. No, it's isothermal, so you can pull T out. Okay, so there's my W. Okay, now your question.
Q equals negative W, so Q is that positive.
That's right. Q is that positive. So it's like already integrating here. You're going to have delta S is Q reversible over T, but you know what Q is. So just substitute in what it is. The T's will
Cancel out.
cancel out.
Just NR, ln VF.
So NR, natural log VF over VI. Or V2 or V1, whatever you like. It's horrible. What the heck? Okay. what's the difference between 4 and 5?
You have the vinyls, you have the volumes, and you have the pressures.
Yeah, so that's the only thing that changed. So what you're going to have to do for this one, I think, is go through all the same work. And you end up with this relationship. And then if you play around with the ideal gas law, you can substitute in the P's, right? So to go from this step to your final answer, you need to set up an equation involving the ideal gas laws. V1s and V2s and T1s and T2s and P1s and P2s, right? Remember setting that kind of thing up on both sides. Cancel what you can, and you're going to get a relationship. Solve for V2 over V1 and see how the P's look, and then substitute them in. So try it. So first you got to go through all the same working. It's up to you whether you want to do all that again. But you would have to if I asked for it. But see if you can convert this final relationship in order to relate pressures, initial and final pressures, when you know initial and final volumes. It's isothermal. So your T's will cancel.
And would your N's be different?
N is, yeah, they never add or subtract gas. So N never changes.
But V? V1 and V2 or not?
Yeah, they're going to change.
Okay. Yeah, because it's compression or expansion.
Yeah. Okay, so Px is nRT over V. So you pull the nRTs out, then you end up with the integral of 1 over V.
But from this to this, did you
Oh, 'cause
derive
P-
this from PV equals NRT?
Yes,
Okay.
yes, from PV. So PV equals nRT. So P is going to be nRT over V. Yeah, we should have wrote that in up there. Yeah, we skipped that. That's not a very good derivation if we skipped that, right? Where was that? That was right here. Yeah, we should have had that.
Yeah, it's going to be P2 over P1, right? Because you've got V2 on top originally. So, no, wait, yeah, Melissa's right. Because you've got to have V2 on top. So that's going to make your first fraction have P2 on the bottom. Yeah. And then yeah. Mhm. That's V1 over V2, and we have the NR on one. And it's, V2 over V1, and we have NR, P1 over V2.
All right. Do you agree?
So no homework on this
Yeah,
over.
you have an easy day. You just have to do bold words.
Nice.
Alright, what you guys?
Just bold words for next class. And there's no homework with this concept to do.